This is Experiment 1, Basic Techniques, and I'd like to talk about how to fill out Table 4, the Summary Results Table. And I'm going to go over the calculations for the first column using the 3.0 milliliter pipette to measure out 2.0 milliliters. You should have, and I've got both my blank Table 4 and somewhere around here, yes, I've got my table of values for Table 1, and that includes my beaker, my temperature of my water, all my masses, and I've already done my density calculations. And I know this is in the next page, but I just wrote them here. I've gone ahead and done my calculations for density according to significant figures, where there's only 2 significant figures for the volume of water. Now, as far as Table 4 goes, see if we can fit some of this back. All right, there we go. Our temperature is going to be 22.5 degrees Celsius. And the correct density is in a table in the lab as well. And so look at that table. The way you read that table is you'll go to 22 degrees, and you'll go over to 0.5 degrees to get to 22.5. And your correct density of water is 0.997655. And that's in grams per milliliter. The experimental average density of water is going to be the average of our 3 values. Our 3 values are 1.00, 0.990, and 0.985. To average those, I'm going to take those 3 values. Let's see here. There we go. And 1.00 plus 0.990 plus 0.985. I get 2.975. And in fact, let's stack them up. So 1.00, 0.990, 0.985, and there, and there. Then we add those up, we get 2.975. We can see that our top number has the fewest number of decimal places that are significant. We were just carrying this extra 0 anyway. And so our answer will be 2.975 rounded up to 3.0 to 2 sig figs. Or what I would suggest is that we just carry 2.975 as our number with the second significant figure underlined. Then we're going to divide that by 3, and we get 0.99166. So divided by 3 equals 0.9917. We still only get 2 decimal places, grams per milliliter. And since this answer is our final answer for the experimental average, I am going to round it, or sorry, cut it off at 2 significant figures. And my experimental average density of water is 0.99 grams per milliliter. Now the standard deviation calculation, that's going to take the average value minus each of the individual values, take the square of those. Let's go ahead and go over that. So for my standard deviation, let's do that right here. So I've got my average value of 0.99. I've got each of my other values. So the standard deviation is going to be equal to, and I'll put my square root symbol in a minute. It's going to be equal to 0.99, and I'll leave out my units for the calculation part, minus 1.00 squared plus 0.99 minus 0.99 squared. We can leave that 0 in there. And then the 0.99 minus 0.985, that's squared as well. Let's get it on the page there. Divided by the number of values. We have 3 values minus 1, so 3 minus 1. And then that whole thing gets square rooted. So let me go ahead and do that. 0.99 minus 1, which is negative. Square it. Plus 0.99 minus 0.99. This is just 0, so I'm not going to include that. I forgot my plus sign right there. Plus 0.99 minus 0.985. I messed up my calculation because I did not use parentheses. So let's try again. So parenthesis 0.99 minus 1, unparenthesis squared. That's a 0 plus parenthesis 0.99 minus 0.985 unparenthesis squared equals, that's this top part here. Now I'm going to divide it by 2, and then I'm going to square root it, and I get 7.9 times 10 to the minus third as my standard deviation. Which, if I wrote it out in regular numbers, would be 0.0079, and which, for our purposes, since our 0.99 only goes to 2 decimal places, we're going to round this to 0.01. And that is our standard deviation. That is the number. We are going to put that right here, 0.01 grams per milliliter. And for standard deviations, it is plus or minus. So that's the calculation for standard deviation. You find the sum of the square of the differences between the points, if that's not too complicated to say. And then you're going to round it so that it becomes at least, so only to the number of decimal places that you have in your average value. So we have experimental 0.99 grams per milliliter plus or minus 0.01 grams per milliliter as the average and standard deviation using our 2 milliliter pipette. We won't be able to rank precision, but when you do rank precision, you're going to be looking at the standard deviation. So because precision is related to how precise you can be when you do the same thing 3 times in a row, and that's what you did down here. So most precise equals standard deviation closest to 0. I'll just write that in here. When you think precision, think about standard deviation measurements. The percent error is going to be experimental value for us, 0.99 grams per milliliter, minus the correct value, 0.997655 grams per milliliter, over the correct value, 0.997655 grams per milliliter. And for this one, I am going to go back and use my 0.9917. Actually, I don't think it matters. Yeah, well. No, it won't. All right, and so when I do this, I will get the following values. 0.99 minus 0.997655, and I'm going to shift my calculator into regular numbers, divided by 0.997655. And I always forget this part. Times 100%, that's what it says, times 100%, numerically times 100. And I get, so this will leave me with just one sig fig, and so I get a negative 0.8% error. And my percent error goes in here. And the only units on percent error are percent, because you can see that our grams per milliliter cancel out. And then when you evaluate accuracy, so the most accurate has the percent error closest to 0. And for this one, so the percent error can be negative, the percent error can be positive. Remember, you're always taking your experimental value minus the correct. That led us to a negative percent error. That means that our experiment was lower than the correct value. You would get a positive error if your value was higher than the correct value. And in this course, signs matter, and we will always keep them. So this is a negative 0.8% error. And once you do all three of them, you can establish which is the most accurate, which is the most precise.